talk to you about topics yet.
And no one's covered any topic 3 so
Alright. Shit. If you don't mind the background noise, I'll try and cover something.
Tim, we're figuring out. We're almost there.
Tagan's trying right now.
I'm testing something. If it works, then we're okay.
Alright, that's good. We're gonna figure this out eventually.
Yeah.
Yeah.
Yeah, the stream audio should be me. Because my mic's muted. Well, it's gonna be super late because lag. Hello.
Hello.
Hi.
You just give me a sec. I just need to share my screen, right?
Alright.
Alright. Does this work?
Wait. It's taking a while to load. There it is. Wait, there it isn't. Jesus, why is this so fucking laggy? Okay, wait. Let me try to remove as much lag as I can. Alright, theoretically, EMS should be able to hear both you and I and see the screen.
Wait, Ems, can you see this?
EMS,
I'm on a call with you.
yeah, EMS confirm at some point.
Alright.
Because there's gonna be like... If so, then we should be fine to post the stream link.
Figure this out before I start.
Yeah, a bit of testing, but it's okay, don't worry. Okay, perfect. The only problem is that we're just gonna have a bit of latency if people ask questions. Worst case scenario, we just answer them later.
Wait,
Okay.
questions will be asked on VC, right?
Nah, we'll just tell them to ask them in chat so we can answer them later eventually. Because if it's VC, it's gonna be so messy.
Wait, so how do I just show this part? Okay, then give me a sec. I need to head to the link on my phone.
Yeah, you can keep the stream open on your phone just to see where we're at.
Yeah, I'm just pulling it up.
Okay, tell me when you're ready.
Sure, just give me a second. Should be good to go soon. Oh dear. Alright, I think.
So we should be good to go to share the link with the chat.
Yep.
Okay,
Oh my god. Thanks, Kaus.
Of course.
Oh my god.
Please load. Okay.
Finally. Oh my god. Hello?
Hi. Okay, I'm gonna mute myself so you can talk.
Wait, can you hear me? Alright, is the audio clear? Hi. Testing. Alright, so you can hear me, right? Testing. Okay, so Unit 3 is all about periodicity. Unit 3 and 13. So the first part to the unit is 3.1, which talks about the periodic table. Okay, so Unit 3 is all about periodicity. Unit 3 and 13. So the first part to the unit is 3.1, which talks about the periodic table. All right, so some basic information before we start with 3.1 is that the columns of the periodic table, that is these things, are the groups. Unit 3 is all about periodicity. Unit 3 and 13. So the first part to the unit is 3.1, which talks about the periodic table. All right, so some basic information before we start with. Okay, so let's begin with 3.1. So essentially, in the periodic table, we have four major blocks: the S block, the P block, the D block, and the F block. So the S block uh, contains the elements whose valence electrons lie in the s orbital. So these are namely groups 1 and 2 as indicated in the above table. The p block contains the elements whose valence electrons lie in the p orbitals. The d block are the elements whose valence electrons lie in the d orbitals. And the f block are the lanthanoids and actinoid series whose valence electrons lie in the f orbital. So now, going back to the periodic table, let us talk about metals and non-metals. So the elements that lie to the left of the staircase are typically metal groups, and then the metals to the right of the staircase are largely non-metals. There are a special class of elements known as metalloids which have the characteristic of both metals and non-metals. So the metalloids, the elements that are metalloids include boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. All right, so let's move to 3.2. Now 3.2 largely deals with periodic trends. So elements in the periodic table are arranged to highlight how its properties vary across a period. So the trends we'll be going over in this session are atomic radius, ionic radius, ionization energy, electron affinity, electronegativity, metallic and non-metallic characteristics, and the nature of oxides. Okay, so before we delve into these into these differences between the physical chemical properties, we need to understand what is effective nuclear charge. So, nuclear charge essentially depends on the atomic number of the elements. So, the atomic number of the elements, as we've studied earlier, highlights the number of protons present in an atom. But effective nuclear charge considers how strongly a nucleus can retain its valence electrons. So, as we can see in this diagram, in an atom with many electrons, the repulsion between inner electrons and outer electrons reduces the attraction between the nucleus itself and the outer or valence electrons. So, the effective nuclear charge experienced by valence electrons is less than the full nuclear charge due to a shielding effect. So, the trend in the effective nuclear charge is that the effective nuclear charge increases across a period but decreases down a group. It increases across a period because the number of protons increase and electrons occupy the same principal energy level. But it decreases down a group as the electrons go further and further away from a nucleus. And as mentioned earlier, the shielding effect reduces the effective nuclear charge. Now, moving on to atomic radius. Atomic radius is measured as half the distance between two neighboring nuclei of an element. The trends that we observe for atomic radii are that atomic radii decrease across a period. Since electrons in a period occupy the same principal energy level, the attraction between the nucleus and outer electrons increases, while with increasing nuclear charge. However, atomic radii increase down a group. Since the number of occupied primary electron shells increases, the atomic radii down the group decreases. This is due to the shielding effect exhibited by inner electrons.
Buongiorno papucia.
Hallo.
Eigenlijk zit ik aan man, ja, voor je man.
Okay.
So now we move on to ionic radius. So ionic radius is essentially the radius of the ion formed by the element. So some key things to understand are that positive ions are smaller than the parent atom. Due to there being fewer electrons, there is more effective nuclear charge, meaning that the outer electrons are held stronger by the nucleus. Negative ions, however, are larger than the parent atom. More electrons means that there's less effective nuclear charge due to increased electron-electron repulsion. Ionic radii decrease across a period for positive ions. For groups 1 to 14, the electronic configuration is the same. The term for this is isoelectronic, but nuclear charge increases across a period. Therefore, the attraction between the nucleus and electron is greater. This leads to a decrease in ionic radius. Ionic radii decreases across a period for negative ions. Electron configuration once again is the same, isoelectronic, but the nuclear charge increases across a period. The attraction between nucleus and the electrons is greater. So it pulls the electrons closer and the ionic radius decreases. Are there any questions at this point? All right, moving on to ionization energy trends. So a key definition we must understand for ionization energy is the first ionization energy of an element. The first ionization of the energy, the first ionization energy of an is the amount of energy required to remove 1 mole of electrons from 1 mole of gaseous atoms in the ground state to form 1 mole of monopositive ions. As we can see in the equation below, the removal of 1 mole of electrons causes element X to become X plus. So there are largely two general trends that can be identified for the ionization energies increase across a period. The increase in effective nuclear charge causes an increase in the attraction between the valence outer electrons and nucleus. Therefore, more energy is required to remove the electrons, leading to higher values of ionization energy. But ionization energies decrease down a group. The valence electrons get further away from a nucleus, that is, they occupy an orbital that is further away from the nucleus. And due to the shielding effect, the effective nuclear charge experienced by these outer electrons decreases. There's less attraction between the nucleus and outer electrons. So this causes a decrease of ionization energy down a group. Anomalies in the trend, such as decrease between beryllium and boron, are evidence for the presence of electron sublevel. As we can observe, hydrogen and helium occupy the 1s orbital, while lithium occupies the 2s orbital. Hence, we observe a huge dip between helium and lithium. This is because the valence electrons on lithium are further away from the nucleus. It then increases for beryllium due to the addition of another electron in the s orbital. But why does it decrease for boron? With electrons entering the 2p with electrons entering the 2p orbital, the attraction between the nucleus and the electron decreases further, causing a slight decrease in ionization energy. Moving on to electron affinity. The first electron affinity of an element is the energy change when 1 mole of electrons is added to 1 mole of gaseous atoms to form 1 mole of gaseous mononegative ions. As we can see, element X becomes X minus in the gaseous state with 1 mole of electrons added to it. There is no exact periodic trend for electron affinity, but it appears to get more exothermic with increasing number of atoms. Since group 17 elements have incomplete outer energy levels and very high effective nuclear charge, it attracts the electrons the most. Group 1 metals, however, have the lowest effective nuclear charge and so attracts the electron the least. This also explains the tendency for why group 1 and 2 elements tend to form positive ions, while groups 7 form negative ions. So, electronegativity of an element is a measure of the ability of atoms to attract electrons in a covalent bond. The electronegativity increases across a period. The greater nuclear charge results in increased attraction between nucleus and bonding pair. Electronegativity decreases down a group. Decrease in effective nuclear charge and bonding is through electrons furthest away from nucleus, so there is less attraction. Now let us move on to the trend in melting points. So essentially melting points decrease down 1 as metallic structures are held together by attractive forces between the sea of delocalized electrons and the positively charged ions. But however, due to the size of the atom increasing, the distance between the electrons and the nucleus decreases, causing a decrease in melting point. But melting points increase down group 17. The London dispersion forces between molecules increase with the number of electrons. That is, as the atom gets bigger, it exhibits stronger intermolecular forces, which we touched upon in chapter 4 and 14. So melting points generally rise across a period, reaching a maximum at group 14, as we can observe with carbon, and then subsequently they fall to reach a minimum at group 18. So group 18 is a very special group as it contains the noble gases. So noble gases are considered to be the least reactive elements, and the characteristics are that they're usually colorless gases, they're monoatomic and very unreactivity. So the reason why they're unreactive is because their electrons form a stable octet, with the exception of helium. Helium has a complete principal first energy level with 2 electrons, while the remaining have about 8 electrons in their outer shell. Other groups lose or gain electrons to achieve the stable octet state. The chemical properties of an element, therefore, are largely determined by the number of valence electrons in the outer shell. Moving on to group 1, the alkali metals. Before we begin with our discussion on the reaction of alkali metals and its properties, I would like to show you a little video on the reaction of group 1 metals with water. So the graying of the element itself highlights how reactive the alkali metals are. Therefore, they're usually stored in oil to prevent the contact with air and water that causes the formation of silvery oxides. Wait, I am on the call. So I wanted to talk about the alkali metals. So these are silvery metals. So these are silvery metals that are too reactive to be found in the natural state. So in laboratories, it's important to store them inside oil to prevent the formation of oxides or hydroxides that causes a layer around the element itself. So alkali metals are good conductors of electricity and heat, as are metals. They have very low densities and they have gray shiny surfaces when freshly cut with a knife. The chemical properties are that they're very reactive and form ionic compounds with non-metal. To highlight the reactivity of alkali metals, we usually consider its reaction with water. So alkali metals react with water to produce hydrogen and metal hydroxide. So while lithium reacts slowly and floats on the surface, keeping its shape, sodium reacts vigorously, causing the surface to melt, forming a small ball that shoots around the surface. Potassium reacting with water causes sufficient heat, that is, it's exothermic enough to ignite the hydrogen produced. This creates a lilac colored flame and it moves more excitedly on water surface. As indicated before, they react to produce hydrogen and metal hydroxide. Hence, we get the name alkali metals. Group 17 or group 7 in Roman numerals is the group of halogens or halogens. The physical properties are that they're colored, they show a gradual change in phase. So, fluorine and chlorine are gases, bromine is a liquid, iodine and astatine are both solids. The chemical properties are that they are reactive nonmetals and reactivity decreases down the group. They form ionic compounds with metals and covalent compounds with other nonmetals. This reactivity trend is explained due to its high effective charge, which exerts a strong pull on electrons, highlighting its tendency to form negative ions. A good way to remember the properties are to understand the properties of group 1, because in group 17 there's a reversal in trends that follow in group 1. Halogens react with group 1 metals to give rise to ionic halides. So the group 1 element donates 1 electron to form a halide ion, and the resulting ion have a stable octet of noble gases. The electrostatic forces of attraction between the oppositely charged group 1 positive ion and the group 17 negative ion bonds the ions together. To understand the properties of halogens or what halogen is present in a given salt, we consider displacement reactions of halogens with with silver nitrate. I did have a video, so I'll share it with you guys so you can watch it for yourself. So the halogens form insoluble salts with silver. Adding a solution containing a halide to a solution containing silver ions produces a precipitate. So sodium fluoride, since it's soluble, so silver chloride tends to form a white precipitate. Silver bromide has a cream precipitate, and silver iodide has a yellowish precipitate. Let us move on to the acid and base nature of the period 3 oxides. This is very important as the metallic and non-metallic characteristics are rather relevant to this. So in the third period, it's sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. Sodium and magnesium form basic oxides. Aluminium oxides are ionic oxides with some covalent character. Thus, they form amphoteric oxides. Amphoteric oxides are oxides which show the properties of both acids and bases. Moving on from group 14 to group 17, its oxides are acidic. So basic oxides of group 1 and group 2 elements react with water to accept hydrogen ions as they are bases, while acidic oxides tend to liberate hydrogen ions, forming acidic solutions. Amphoteric oxides do not affect the pH when it is added to water and is essentially insoluble. It is said to have the properties of both an acid and a base, as indicated earlier. That is all for Unit 3.1 and 3.2. If you have any questions, let me know in the chat. If not, I'll be passing the stream on to Ems, who will be conducting the AHL part of this, 13.1 and 13.2. Thank you, guys.